Hello and welcome to my Game Boy Color Sprites topic. So in this video I'm going to cover all about Game Boy Color sprites and using them in an actual game. This is kind of a game, I suppose. You can play and win this game. I've put some sprites together to make up game actors. So first off, I will show you what we have. So if I press A to start, you'll see our character here and 3 enemies. So the character is actually consisting of more colours than a single sprite can actually have. And to create the illusion that we've got loads of colours on our character, I'm actually using a process called sprite layering, where we layer sprites on top of each other to give us the extra colours needed. I will get into that in a moment. So what I've also implemented as well is, so we have a mini level here, and there are player to background collisions in our level as well. And I also have collisions for the player hitting an enemy as well. As you see, hitting an enemy will lose a life and reset you back to the top right. The aim of this game is to make it through to the left hand side here. So every time this game restarts, the spaces to get through will randomly change to a different location. Sometimes you'll be able to complete the level, other times it'll probably be too difficult. So if I attempt to complete this, well, I'm not going to be able to complete this. Because the fish here won't go down far enough. There you go. So I should be able to complete it this time. Anyway, I'll come back to this later on. So first off, I'll show you how sprite layering works. So when you design sprites, you can actually layer them on top of each other. So this is the main player from this game. So you'll see the bottom layer has 4 colours, and the layer above it has another 4 colours. So there's 2 palettes to make up our character here. So the Game Boy Color can have 10 sprites on one horizontal line. So depending on how much action you intend to have in your game, kind of depends how many colours you can have for an actor. So, and also the size of your actors as well. So for this character here, these are 16 by 16 pixel characters. So he uses 4 tiles, and the sprite mode will be 8 by 16 for this character. So we actually use 4 sprites to create our character here, so that would leave 6 sprites remaining. So if you don't mind sprite flickering or sprites disappearing, then you could have as much as you like. But when there's more than 10 on one horizontal line, some will start disappearing. So you'll need to kind of limit what you decide to kind of use. So if I show you some of the actual graphics here for our main character. So these are the animation frames, and then this is the top layer, and this is the bottom layer, and you can see here the two palettes. So if you made him any bigger, then you would have to try and control how many sprites would be on the same horizontal level as our main character. Obviously, as you design the games, you can decide yourself. You can have bigger characters, but you will obviously have to have less action happening on the screen at the same time to prevent sprite clipping. And this is what it looks like when both of the layers are applied. So when you actually draw these sprites as well, you do need to prioritize the sprites. So on the Game Boy Color, there is a priority when sprites overlap one another. So the lowest number sprite appears above the highest number sprite, which is why you need to give these a lower number than these so that they appear above them when drawing them on the screen. I'll show you briefly some of the other character graphics in the game as well. So you've got the fish character and the bat there as well. So you can, if you create some more palettes, you can literally reuse these graphics again, but just substitute these colors for some new ones and then redraw the sprites with a different palette. So the sprites, when you draw them, there is an attribute byte that you use for them as well. So you not only have to pass the tile ID of the graphic, but you would also have to pass, or you can pass, an attribute byte, and that attribute byte is split into bits. The bottom 4 of those are used for the palettes. No, sorry, the bottom 3 are for the palettes. The top 2 bits are used for flipping the horizontal or vertical tiles of the sprite. So when you draw these sprites in this project, I will be creating them using 8x16 sprites. So just make sure when you actually convert these with my graphics converter, if you are going to use that, to make sure you set the blocks to 8x16. And the background tiles for the game look like this. So these here, I consider these as the walls, if you like. So although the game is called the Crate Escape, you can actually switch the crates out for boulders or mushrooms, and there are some coin graphics in here as well, which I haven't used, but I will leave these in here so you can play around with those in your own project. You could also replace the lives in the game with beating hearts as well. One thing I've done in this game as well is replace the starting tile with this one here. So everywhere tile 0 is drawn, it will appear to be a floor. So this is a seamless tile. What that means is it repeats in every direction. So if I show you something that you can do in Libre Sprite. So here's our tile here, and we can go into tiled mode and put it tiled in both axes. And now we can design a tile to be a floor pattern. So if I show you what happens here, you could play around to create a whole load of different patterns for floors for a level here, and then check with this setting here can give you a good idea whether it's going to tile seamlessly or not, which is very useful. So that's our tiles. So with sprite layering you can, although I've only used 2 in this case, with careful organisation you could obviously add in more colours to not only the player but also the enemies as well. In this little example, the enemies don't use any additional sprites for themselves, but on like a large sort of scrolling game, you're only going to have maybe 1 enemy or 2 on screen with your character at any one sort of time. So you could go overboard with as many colours as you can kind of get away with. So one of the next things I'm going to go on to is the collision method used. So in this project, the collision types I've been using are rects, or rectangles as you would call them. So this is what the structure looks like. We literally record the top left position and the width and height of our rectangle. And then using this structure here, it then enables us to easily check whether objects have collided. So this is the collision code here, where you check to see whether 2 rectangles, or rather the actual thing is you check to see whether rectangle 2 is intersecting with rectangle 1. For example, if any of this happens to these rectangles here, if R2 appears in R1 at all, then we return the value true, otherwise we return false. So these 2 rectangle structures are passed by pointer here, so they're basically passed by reference. You're passing the address of them, and then in here these are temporary variables which are used to hold the positions passed in the rectangles. For example, x1 is used for the first rectangle there to hold its x position, or rather its left position if you like. So you can think of the dot here as the sort of origin where this rectangle would be set, and then W1 here is the width. So the width is actually the X position plus the width, which is recorded in W1 there, and then W2 is rectangle 2's actual width, and then H1 just takes the height. H2 is the height of the second rectangle, and then you just check in to see whether parts of them intersect with one another. So in this case, if the width here is greater than the starting position here of the second rectangle, and if x1 here is smaller than the width position of rectangle 2, and also if the height here is greater than the starting height of rectangle 2. So this is the most common method I use in all of my games for collision detection. And if we use this character here, so what you would do is you would make sure that the X and Y position correspond to the actual location of your sprite, or rather where it would be on the actual screen, and then you make sure the width touches the leftmost side, if you like, and the height is basically the bottom of your character. You want it basically fitting as snug as you can to the character, so that it appears that collisions are fine. One thing you can always do as well, when you're looking to collide with different enemies, is you can shrink the collision rectangle so it's just a bit smaller than your character. That way you can kind of have some sort of leniency when two objects actually collide, but you wouldn't want to do that with colliding with background tiles. In this project here, the levels are also split into rectangle tiles. So if I show you the actual level map here, which is this here, each of these ones actually represent a wall. So what we would need to do is work out where all of these walls are and create a rectangle that bounds those walls, and then we check to see whether we've collided with that wall, and if we have, then we obviously stop the player from going through that wall. Anyway, I'll get to that in a bit. So now I'll move on to another thing that's key in this program as well, is game states. So first off, I will jump to the main part here, and I will split this up. So the main function in this program here, you can see, is literally nice and clean here. This is what I do for all of my completed games, and it uses a simple sort of state machine where we have our one variable here, which is main state, which is the main program state, and then I use an enumeration data type here to limit the states the game can have. In this case there's only 2 states, but if you had like a large game you might have more than just the 2 states. For example, you could have like a high score state which you might want to have if the player has scored a certain number of points. Then you would use that to transition to that state. So what I have in each of these states is I have an initialize part and a run-in part to keep it simple. And then each of these states, then the function prototypes for them are declared in the main header file here. And these are then implemented in the modules which will house those states. So in this program here I've got the 2 here, so there's the I'll label them with MS to show that they are main states. So this is a typical example here. You've got your main loop here with your main states. I always update the controls outside of all of the states here, so you would also put other things outside of the states which aren't really applicable to them. There could be a sprite routine running here as well, but I've obviously not included it in this. So each of these functions then might call a number of different functions themselves, which obviously doesn't need to be known about in the state loop here. So for example, in initialize game here, in all games you would probably first off set the score to 0, then you would set the lives variable to however many you deemed to be the right number you wanted your player to start with, and then you would prepare the world that the game was actually going to take place in. So that might be loading in the graphics for the world if it was using just one set of graphics, or it could just be setting the level to level 0, and then you would then maybe initialize the graphics for level 0. Maybe you have a load of different music you might want to load at the start of your game as well. This just for me, this is the method I've been using to easily separate the states of the game into blocks to make it easier and more logical to deal with. If you need to add anything extra in, just add some more states with an initialize part and a run-in part. So that covers the these few topics here I wanted to cover. I will now jump into the code and try and go through some more bits and pieces which are included in this. So I've covered the main states here. So let's go into the individual parts. So I'll start off with the title screen here. So if I bring this across here, and if I run the project again in Emulicious. So to start off with, we go into the title screen initialize phase. And then what we do here is we clear the screen each time. So this would be called at the start of the program, and also if you die on a game as well, then it would reset back to this state here. Same if you won the game, it always would come back to this. So in this case, what actually happens is it draws up the mock title graphics, if you like, just draw in the crates and the floors. And then we have the blinking text here. So this is a global variable which is only used, well, sorry, it's a local variable that's just used in the title screen class itself. Same with the this timer here for handling the blinking of the text. So this function just, if the blink on is true, then we draw the text center in the screen. If not, then we print a load of spaces to that part to erase them. And another key thing which is used here as well is because the game relies on random numbers, you kind of need to seed the random number generator. So if you do not seed it with a unique number at the start, then the game random number generator will basically create the same numbers every time. So to get around that, I have a variable here which, while the game is stuck in the title screen part here, it's constantly changing the value of this. So once we've gone down here, we've initialized the manage blink bit first, just to at the start we set it to true to draw everything the first time round. We then change the state to title screen run. The program would then go back to here, draw one time. So the title screen init function and the game init function, they only run one time, if you like. Then they should change the state to the running state. And then you'll see here, every time this is called, it updates the seed value, and then it just handles the blink. And then all we're looking for in this function here is if you press the A button, then we change the main state to game init to start the game. But first off, we initialize the random number generator with whatever value is in seed. So if I go down to that here, what I also do as well to add in an additional thing is OR the value of lseed with the value in the div register, and then pass that to the initialize rand function. So that's the title screen part. Now I'll dive into the main game part. So there's a number of interesting things in here. So one of the things I've not done from this game is to put the player or the enemies into their own modules. If a game was any bigger, then that would be a worthwhile thing to do, so that their initialization and updating each time the game runs would be outside of the main game code here. But as this is kind of a one level program, I haven't done that this time around. So some of the things you should notice here is each character needs to have its own collision rectangle. So that's the player one there, and then each enemy has their own collision rectangle as well. So every time these all move around, we then need to check to see whether they actually hit each other or not. This is a function I left in. So sometimes as you go through these projects, the more complicated they get, sometimes you'll have problems with things running and you might need to try and debug them. For me, it was just making sure that the values of some of the collision rectangles were what I was expecting them to be. In the case here, this is these are the collision rectangles from the level manager class, which I will cover shortly as well. So I'll give a quick brief overview of some of these commands here as we go along, and functions. So the initialize player function here, the player always starts at tile 8, so each of the background blocks here are 16 pixels wide, so you can think of the screen, if we are working with 16 by 16 tile blocks, then you can consider the screen to be made up of 10 by 9 blocks. So this also allows me here to explain the level design as well. So just like you design characters with their own palettes, you can design levels that way as well. So if I bring back these here, so each of these blocks or these pixels here in the game will represent a 16 by 16 pixel block or 4 tiles. So one of the things I do is I create like a palette which represents the game blocks in the level. So the level in our case here actually looks just like this. In fact, I'll just double check that I've actually got that looking right a minute. It looks something like this anyway. So we've got oh wait, then that's why it's actually supposed to be that size. There we go, now that looks right. Anyway, it's not really important how the accuracy of this. So this is how I kind of design levels here. So what I could have done was I could have had more things in the level data here. So if I bring that back in, this is what it actually looks like here. This is the level data map. So here, wherever there's a 1, it's actually a wall in the level. So you can use these levels for you can use these level maps, as means to draw the level, and also ways to check for collisions with walls in the level as well. So you could, for example, create like a palette here, if you like, of for example, say the green color is the player where he will start, and the red color is where the enemies would start. So you could, there you go, there's where the enemies will start in this level, and the player will start here. And then to export this, you could literally just go along filling out an array like this, and then match the numbers here to where they are on the grid here, and then that's your level there. That's a quick and easy way to make these levels. And then using these levels here, you can then use those to draw the actual level. So in the level initialization function here, what we do is we use a pointer to point to the start of the level. As there's only one, we point to byte 0 in the level array or level map, and then we just iterate through the width and height. Treat this as a grid of tiles here. So in this one here, you'll see this variable here is how many blocks go across in our level, and this is how many blocks go down, which allows us to do this here. So we've got screen height here and screen width. So by doing things like this here, it means we could import this code into a different project for another console, and then we could just change the numbers here and then rebuild it for whatever console. So there's only 2 tile types in this level, so it's nice and simple. There's 1 which means a wall, or 0 which means a gap. So we get a byte from the level. If it's a 0, no, sorry, if it's not 0, then we draw a wall tile, and then we add a 1 to our collision map as well. So the collision map is another array that duplicates this here. So this is obviously constant here, but the collision map will need to be in RAM so that it can handle whatever level you decide to draw. And then if it's a 0, then we obviously plot 0 in the collision map and we don't draw a block in that place. So each time through we increment this value here, TD. So TD is a variable that is used to point to the tile in the collision map as well. So it's kind of mirroring what's in the level. And then once we've drawn all the walls in the level bit here, we then put in random spaces on the wall parts. So wherever there's a strip of walls, we generate a random Y position along that strip, and then put a 0 into the collision map, and then clear the tiles on the screen where that wall is. And then once we've got to this point here where we've drawn the level and drawn the spaces for us to walk through, we then need to fill out our rectangle collision list. So what this does here is it goes over the collision map and then builds a load of rectangles. So this is kind of complicated. What it actually does is wherever it finds a 1 in the collision map, it then records the length of those 1s and interprets them as being a rectangle region, and then records that using this function here. So it's kind of complicated. You'll have to probably look into this to kind of get a good understanding of what it's doing, but basically all it's doing is it's creating rectangles from the wall regions it finds going across the collision map. So if you create a new level in here with more walls, you may need to change this number here. So this is a fixed array here which only holds 34 rectangles at present. I tend to not dynamically allocate arrays on the Game Boy. On some of these smaller consoles, try and if you're not sure how big to make an array, then run the program a couple times first with maybe the biggest object or level that you intend to use, and then record the value of the array size as the maximum that you'll need. That way you don't have to use expensive malloc and calloc functions to dynamically allocate arrays. So this builds the collision stuff here. Not going to go into any more detail with that, just have a play around with these things. So one thing that's in here, there is a debugging function in here when you are building these rectangles here. So this is another function I put in here which I use on a regular basis everywhere on all the different consoles I use, as it is extremely useful. So I will cover that now, and that is this function here. So sometimes as you're running the program, you might have all kinds of issues and you're like, well, why isn't it running? And that's where this program here comes in. So what this function here does is it simply displays the string here that you pass to it on the top of the screen, and then it will print out the error number, and then it will just stay in a loop. So it deliberately crashes the console in a fixed manner, but it displays the error message for you so you know where the error occurred. For example, if you were unsure how certain things react together in your game, you might want to add this as a kind of breakpoint. Or if you are unsure if a character went outside of a level somewhere or something of that nature, then this would be a perfect thing to use to kind of track and debug that. sometimes you can just use, well, you could just use it anywhere you see fit to include like a breakpoint. So let's have a look what else I want to cover here. I think I've probably gotten into most stuff here now. So key things to note from here. So this here, when you call the level init function, these are just values that you can pass in here, and then it will draw the graphics every time it finds a wall in the map. It will draw these tiles instead of the crate, which is the default in the game here. So going back to the game states part here, so when you call the game init function, this is what happens here. So it sets the score to 0, sets the lives to 3, and then it calls this private function here, game reset, which is this here. So this function here is also called when the player dies or if a level is completed. You kind of in the game initialize part, you just kind of set the global game variables, if you like, and then then you kind of would call like an equivalent sort of function as game reset here, which would just restart the starting positions of everything, and then redraw the lives, score, all that sort of stuff in a game. In this case, what happens is it resets the player sprites to the starting position here. And it does the same for the enemies as well, although they let's have a look. I wasn't sure whether I'll give them random positions or not. Which I didn't. And then there's also various things in here as well. So this little array here is just used to handle the player's movement here. So as you'll see, this is like frame 0, that's frame 1, and that's frame 2. So when you're moving, you obviously don't want the animation to look like that. So frame 0 is this start here where he's static, and then frame 1 is where his like right hand is up in the air and his left and his right leg is back. So that handles the animation for the player there, which is a nice little like cheat. And then we've got the animation delays here. That's the maximum amount of enemies I put in. You could obviously change and add more there if you liked. And then the game run is the sort of like main sort of meat and veg of the program, if you like. So to complete the game, all that it does is check to see whether the player's horizontal position is at 0. If it is, then it then prints you win, and then it will keep checking to see whether you press the start button. If you've not done any of that, then it will just return to the main loop. Otherwise, what happens here is the animation timer runs, and then once that has ticked down to 0, then move the enemy and the baddie and the player, and then check to see whether a collision has occurred. If the lives have gone below 0, then it's game over, and then it creates a loop here, like until you no, sorry, it just creates like a new timer, if you like. So it counts down to 0 and then resets the game to the title screen there and returns. Otherwise, if your lives are greater than 0, then the game just resets and then continues on its way. Oh yeah, the game, you can also quit the game by pressing B here as well. I'll leave that in. So this is the function here to handle all of the player to enemy collision here. So it uses a temporary rectangle pointer here to point to the start of the enemy collision rectangle list, and then checks to see whether the player rectangle has collided with the enemy one. If it has, it returns true. If not, it goes through the rest of the list and then returns false otherwise. These are kind of straightforward. There's nothing special about the enemy logic here. It just flips between moving them up and down. As the sprites are made of 2 parts, it handles this in the sprite manager, which I will quickly get into in a moment. The player handler function. So there's more in here. So when you move the player, you'll see that there's this variable here, PL speed. So have a play around with this. Obviously you don't want to put it too high, otherwise you can potentially just walk straight through a wall, because if your speed is greater than the size of a wall, then you can literally just go straight through it. But what you do here is you don't move the physical player and draw him on the screen first. What you do is you use a temporary variable to hold the new position. In this case, we're moving the collision rect only, checking to see whether it hit a wall at that new position. If it does hit a wall, then we end up resetting it back to its old position. Otherwise, we mark the moved flag to true, and then we also alter the player's speed. This is the same sort of thing for all of the movements here. We use this flag here to indicate whether the player is actually moved or not. If the player has moved, then that means we need to update the player's frames and also the player sprite layers. So each of these sprite commands here works on 2 sprites at a time, because the sprites here are made up of 8 by 16, so that's half of the character. We obviously have to work on 2 at a time. So in the sprite manager class here, or rather functions, not classes, I'll quickly go over this a minute. So we use this structure here, and we only create one of them. So this is just a manager structure, if you like. to hold all of our sprites. This code here works on 16 by 16 images or 2 sprites at a time. So the initialize function here sets the sprite mode to 8 by 16. It will then display them or set them to be drawn on screen, and then it will also call the clear all, which will move all of the sprites off screen. So when I was saying here, each sprite in here actually is made of 2 parts. So we use this variable here in the sprite manager to hold the ID of the sprite. So every time we add a new one, we need to update this ID by 2 each time. The structure here holds the ID number of the sprite and its horizontal and vertical position here, and the graphics tile ID. All it's actually holding here is it's holding the ID of the leftmost sprite each time, not the rightmost one. And then these 2 commands here, we use these to initialize the data for sprites and to set the colors in the color palette. So the palette start here, there's a maximum of 8 color palettes for sprites, so that would be 0 to 7, and then palette count does allow you to add more than 1 palette at a time. So that would be, if you were just passing 1 palette of 4 colors, that would be 1. Otherwise, as in the game here, at the start we set the sprites tile data here, and then we set the palettes for the sprites here. So there's each sort of game actor, if you like, has 2 palettes associated with it. So the player has 2 palettes and the enemies have 2 palettes. So you could one of the things you could do is have a play around with the these values here for the colors. So the sprite new command here, what that does is, first off, we check to make sure that we're not trying to allocate more sprites than what we have set up a structure for here to hold. Then we set the sprites details we pass in here. So notice that there's the tile ID and the attribute byte. All I'm focusing on in this game is just the palette numbers in the attributes. I don't really tend to use many of the others, but you obviously can have play around and see how they work here. So one thing to note with sprites as well is their position doesn't actually align with the actual screen on the Game Boy. It's off by 8 pixels to the left and 16 pixels down as well. So to correctly display the sprite on the screen, you need to add 8 to its horizontal position and 16 to its vertical position. The reason why these things are there is so that the sprites can move off the screen borders seamlessly. So first off, we then, once we've got all this set up, we then use the actual sprite ID in hardware, which is recorded in this variable here, which we store in the ID here. This is a number we need to pass to the gbdk commands to work on the sprite. So we've got the set sprite tile, move sprite command with the horizontal and vertical positions, and then this command here, which is set sprite prop, which I obviously haven't used in the normal Game Boy videos. So this is where you pass the attribute byte. These are the three key things you need for a sprite to work with it here. Next, what we do is we then increment the ID number by 1. We then increment our sprite counter variable by 1. And now we draw the right hand side of the sprite. So we add 8 to the past horizontal position here. We add 2 to the tile ID, and then we draw the second half of the sprite, and then increment the starting ID ready for the next sprite. And then each of these just works with what's in our array, and then we'll move the sprites that make up our game objects, or change the tiles or attributes, or hide them. Again, all of this definitely dive in and have a play around with. I think this video's gone on for long enough now, so I will call it here. I will post the code to this on my SourceForge site. Hopefully it will be of use to you. Okay, thanks for watching, and I will catch you next time. If you've got any questions, then obviously leave them in the comments below, and I will try and resolve them.